To make communication easier, let's start using a coordinate system like the one used in school. As you can see, the z-axis runs in the direction of the magnetic field lines, and thus can represent them. So we can stop drawing the external magnet in all other illustrations. From here on, we will also illustrate the protons as vectors, as little arrows. Maybe you can remember, a vector represents a certain force, by its size, that acts in a certain direction of the arrow. The force that is represented by vectors in our illustrations is the magnetic force. Now, let's look at this illustration. Here we have 9 protons pointing up, precessing parallel to the external magnetic field lines, and 5 protons pointing down, precessing anti-parallel to the external magnetic field. In order to simplify this demonstration, let us stop the animation. What we see in the figure is just a picture taken at a specific point in time. A picture taken just a little later shows the protons in different positions because they precess. The precession actually goes very fast. The precession frequency for hydrogen protons is somewhere around 42 megahertz in a magnetic field strength of 1 Tesla. This means that the protons precess around the ice cream cone more than 42 million times per second. Now there are millions and millions of protons in your body precessing this fast. It's easy to imagine that at a certain moment there may be one proton, A in the illustration, pointing in one direction, and another proton, A1, pointing exactly in the opposite direction. The result is very important. The magnetic forces in the opposing directions cancel each other out. Like 2 persons pulling at the opposite ends of a rope. Finally, for every proton pointing down, there is one pointing up, cancelling its magnetic effect. But as we have learned, there are more protons pointing up than down, and the magnetic forces of these protons are not cancelled by others. So we are left, in effect, with some protons, 4 in our example, pointing up. However, not only magnetic forces pointing up and down can cancel or neutralize each other. As the protons that are pointing up precess, there may be one pointing to the right, while another one is pointing to the left. The magnetic force of proton A can be seen as resulting from 2 components. One pointing up along the z-axis, and one in direction of the y-axis. The magnetic force of proton A1 also has a component along the y-axis, but in the opposite direction. Thus, the component of A along the y-axis is cancelled out by A1. The same holds true for other protons. For example, B and B1. For B pointing forwards, there is B1 pointing backwards. They cancel their respective magnetic vectors along the x-axis. In contrast to the magnetic vectors in the xy plane, which cancel each other out, the vectors along the z-axis point in the same direction, and thus add up to a new magnetic sum vector pointing up along the external magnetic field. In this direction, the single vectors, the single magnetic forces, add up, like people pulling on the same end of a rope. Now, what does this mean? This means that by placing a patient in the magnet of the MR unit, or in any other strong magnetic field, the patient himself becomes a magnet. In other words, has his own magnetic field. Why? Because the vectors of the protons that do not cancel each other out add up. As this magnetization is longitudinal to the external magnetic field, it's called longitudinal magnetization. This new magnetic vector is important because it is the one that may be used to get a signal. It would be nice if we could measure this magnetization of the patient, but there is a problem. We cannot measure this magnetic force as it is in the same direction, parallel to the external magnetic field. To illustrate this, imagine you are sitting on a boat, floating down a river. You have a water hose in your hand and squirt water into the river. For somebody who is watching you from the shore, it is impossible to tell how much water you pour out. In other words, how much new magnetization is added in the old direction. However, when you point the water hose at the shore, change the direction of the new magnetic field, then the water may be directly picked up and measured by an impartial observer on the shore. What we should learn from this is, magnetization longitudinal to the external magnetic field cannot be measured directly. For this, we need a magnetization which is not longitudinal, but transversal to the external magnetic field. Before you walk away, let's just sum up, and when you come back, start with this summary again.